We are going to discuss about the remaining problem characteristics. So already in the previous session, we talked about few of the problem characteristics, like whether the problem is decomposable, can the solution step be ignored or undone, whether the universe is predictable, is a good solution absolute or relative. So this is what we discussed in the previous session. So today we will discuss about the remaining problem characteristics. Whether the solution is a state or a path. So what is the role of knowledge? Does the task require interaction with a person? So all these things we are going to discuss today. So we'll go one by one. So before going into this, a short recap of why we need problem characteristics and why not all problems are considered the same. So when an AI agent picks up a search algorithm, okay, so it must first understand the nature of the problem it is trying to solve, okay, because in the real world, not all problems are same. Some problems might be simple and predictable, while other problems might be very complex, dynamic, and it might involve a lot of uncertainties. So, the choices that the agent makes at this stage have a huge impact on efficiency and correctness. Today, with this recap, we will go into the next problem characteristics, whether the solution is a state or a path. So, when an AI agent, when he tries to solve a problem, so what exactly it is looking for? So let's think about it carefully. So generally there are two possibilities. The first one might be a state or a path. So when it is going to be a state, the agent only cares about where it ends up and it is not bothered how it got there. So the final configuration is the solution. So you don't have to bother about how the journey was. That's irrelevant. So we call this as a state solution. Okay. Second possibility is that the agent cares deeply about the sequence of actions to reach the goal. So every step it takes matter. So we call this as the path solution. But this fundamentally changes how the problem is formulated. So how the agent searches and what is considered as success. So we will understand about the state and path solutions with examples. Okay. So first we will start when the solution is a state. Okay. So what the agent should do? The agent only needs to find a goal state. The path taken to get to that particular goal state does not matter. So what are the characteristics? So we have to bother only about the final state. No path cost needs to be tracked. So we don't have to bother how the agent arrived to that particular goal state. Multiple paths may lead to the same valid solution. So we'll look at some of the examples. First, we will start with the problem of n queens. So the problem is we want to place 8 queens on a chessboard. Constraint is no queen should attack each other. So for a state solution problem, does the order of placing the queens is a problem? So absolutely not. We don't have to bother about in what order we place the queens. Like whether we place the queen number 5 before queen number 2 or we started from the top row or from the bottom row. All these things does not matter. We are bothered only about the final board positions or the configuration. Whether the constraint is satisfied. What is the constraint? No two queens should attack each other. So all the queens should be placed. That is, 8 queens should be placed. Suppose if it is an 8 queens problem. So other examples of state solutions are constraint satisfaction problem, where we need to find the values that satisfies the constraint. We don't have to bother about the assignment sequence. That's irrelevant. If we talk about the circuit layout, we need to find a valid arrangement of the electronic components. That's all. The design is not a problem. Okay. So for all these problems, the best algorithms are the ones that evaluate the quality of states directly. So the algorithms can be like hill climbing, simulated annealing, genetic algorithm. So all these algorithms move through the state space without tracking the path at all. So they don't have to remember from where they came. That is the basic idea. Okay. Now we will discuss about when the solution is a path. Suppose the agent is trying to achieve a goal for a path problem. The agent must find the sequence of actions. So every step is a part of the solution. What is step 1? What is step 2? What is step 3? What is the goal state? Everything. What is the steps involved in between state 1 to goal? So when we talk about the characteristics, the full action sequence must be recorded. Path cost is tracked at every step. Order of actions matters, which is done first, which is done second, which is done third. The solution is only useful if it can be executed step by step. Very, very important. Now let us talk about some of the problems. Let us take the first problem as route finding problem. Supposing if I have to travel from Chennai to Delhi. So it's not enough that knowing that you are in Delhi. So you need to know every turn you made, every road you crossed, which all cities you crossed along the way. So this sequence is the solution itself. Supposingly, if you take an 8 puzzle problem, the final board is not a problem. The solution is a list of tile movements. The agent must provide the list of tile that moves from start to finish. Okay, whether you move third tile to which position, fifth tile to which position, everything you should know. If you talk about a robot navigation problem, the robot needs each movement command and sequence. If the robot has to move from room A to B to pick up a tea, then you have to give a proper instruction how many meters it should walk, where it should make a turn, where the teacup is placed. You have to give a sequence of actions that it should perform. For a theorem proving, each inference step must be recorded to verify the proof. So for path problems, we use algorithms that extremely explicitly track and return the full path, like breadth first search, depth first search, uniform cost search, A star. So these algorithms maintain the complete history of actions from the starting state till the current state or the goal state. Okay. Now we will take more examples and we will discuss. So we will first talk about the path problem itself. So we are going the example to be discussed is the 8 puzzle problem. So what is an 8 puzzle problem? So it is a 3x3 grid. You have to arrange the tiles. Okay. The numberings are from 1 to 8. And there will be one blank space. So the goal is tiles should be arranged in order, like it should be 1, 2, 3, 4, 5, 6, 7, 8, and your blank should be finally here. Now, for a path problem, this arrangement 1, 2, 3, this arrangement is not at all a problem. Okay. The problem is how you arrive at this final state. So, what are the sequence of moves involved to get to this particular state? Okay. So, like you have to tell, move tile 3 left, move tile 6 up, move tile 1 right. See, the initial board configuration can be anything. So, from there, how did you get here? It's what the agent must produce. So, without the path, the agent cannot execute the solution. So, what the agent will return, it will not just return the goal state, this state. So, but it has to give the ordered list of every tile from start to finish. It's very, very important. Now, we'll take one more example. Okay. So, it is a classical example from Russell and Peter textbook. So, it's a route finding problem from a particular state like Bucharest, another state to Arad. So with this, Bucharest is the start state and Arad is the goal state. So since again it's a path problem, we should not like, if I'm in Arad, it's not enough. But what is how I arrived at Arad? The path found is from Bucharest to Pithesti. We have some heuristics here, value involved. The heuristic value involved here is the kilometers. Okay. So from Bucharest to Pithesti, it is 101 kilometers. From Pithesti to Rimnisu, it is 97. From Rimnisu to Cebu, it is 80. And from Cebu to Arad, that is the goal set, is 140. So total cost involved from traveling to Bucharest to Arad is 418 kilometers. So here, the solution is not only the Arad, but the ordered sequence of cities or the states that is traveled throughout. So you cannot skip a particular city like Pithesti because your destination is Arad. So every step in the journey is very, very important. So other examples include robot navigation, puzzle solving, like any kind of puzzle, game playing, logistic planning. So all these are example of a path problem. Next, we talked about the state problem. So for an end queen problem, we'll show the board pushing. So it's a perfect example for a state problem. So we are bothered only about the final state. So the problem here is place n queens on an n cross n chessboard. That n can be anything. It can be 8 queens, it can be 4 queens. The ultimate constraint is no two queens should attack each other. Should have no shadows, no columns, no diagonals. Means the queens will attack each other. Why the state only matters here? The agent places the queens one by one during the search process. But the order in which the queens were placed is completely irrelevant. It doesn't have to maintain all those things. If it's going to maintain all those things, then a lot of memory is going to be used. So, only the final board configuration is more than enough. It does not bother about every step. So finally, when you look at the board, a valid arrangement of 8 queens is the solution. So no path cost, no action sequence needed. The agent can place queen 5 before queen 2, before queen 8, anything, as long as the final state is valid. So one of the board positions is 3, sixth column, second column, seventh column, first column, fourth column, eighth column, fifth column. So you can try and place these queens and see if whether the queens are attacking each other. See, you can see the board positions here. First column, seventh column, fifth column, eighth column, second column, fourth column, sixth column, and third column. So the ultimate constraint that no queen is attacking each other. Okay. This particular state itself is the answer. So other examples include Sudoku, constraint satisfaction problem, optimization, finding the minimum cost configuration. So these are the state problems. Okay. Now we will talk about the summarization, that is comparison between the state solution and the path solution. For a state solution, what is returned? What the agent will return? The final board configuration if it is an 8 queens problem. So, is the path cost tracked? No, you don't have to track the path cost. You don't have to track the order of actions, irrelevant. If you are taking the 8 queens problem, you don't have to bother about in which order you are placing the queens. As I said already, anything it can be. It can be N queens, it can be CSP, any problem. The search focuses only on the end state, valid state. The best algorithms that can be used are hill climbing, genetic algorithm. So here, you don't have to maintain the entire path, so memory used here is very low. Backtracking, if needed, optional, it can use it. So the success is measured based on the valid final state. Okay. Now, we'll talk about the path solutions. So we return the sequence of actions. Every step we traverse from the start to the goal state has to be tracked. That is, a path cost has to be tracked. Order of actions is very critical. You have to maintain it. Example, 8% you have to maintain. Which tile you moved, whether left, right, bottom, everything you have to maintain. The route finding also the same. What are the routes you travel? For example, we discussed about Bucharest to Arad. So you have to maintain every state you visited to reach to Arad. So the search focuses on the entire journey. Quality depends on the entire journey. The best algorithms involved here is breadth first search, depth first search, A star, anything you can use. But the only problem is we need high memory to store the full path. Backtracking is often essential. Supposing if you take the same route finding problem of going from Bucharest to Iraq, if I am in the wrong direction, I have to go backtrack and find the solution. Success is based on all the valid state plus the optimal sequence. Everything is important. Now, how or what is the impact on the algorithm's choice? Very, very important. See, these two are problems like path problem and state problem. So you have to use the corresponding algorithms for the corresponding problem. For a path tracking problem, use path tracking algorithms. Algorithms can be BFS, DFS, A star. When you take BFS, whenever you want to find the shortest path, explore level by level, go for BFS. If you have to explore deep and memory efficient problems, then go for DFS. If it is involved with heuristics like your Romanian map problem, finding the path from Bucharest to Arad, if it involves heuristics, use A star search to find optimal path efficiently. If you want to have a low cost path, then go for UCS, that is Uniform Cost Search. All these maintain a record of actions from the start to the current node, or you can say till the goal node. For a state problem, use the state evaluation algorithms like hill climbing, simulated annealing, genetic algorithms. When you talk about the hill climbing algorithms, it moves to the best neighboring state. So no path memory is maintained. When you talk about simulated annealing, it accepts the worst case states to escape from the local optima. Otherwise, it will get stuck in the local optima. When you talk about the genetic algorithms, it evolves the population of state towards the better configuration. So none of these need to remember how the current state was reached. That's a beauty, right? So choosing the wrong type of algorithm, like vice versa, for a state problem, if you use a path problem algorithm, for a path problem, if you use a state problem, you're going to waste your memory, time, and produce useless or unusable results. So, what we discussed here is for a path and a state problem, use the corresponding algorithm for better result and efficiency. The references are from Stuart Russell and Peter Norvig, Parag Kulkarni, and Elaine Rich. Thank you.